Dirk, everyone should be in.
Okay. There's some other people here. Good morning, everybody. Welcome to this week's Quantum Optics and Quantum Electronics seminar. It's a great pleasure to introduce our speaker for today, Professor Jose Capmany from the University Politecnica of Valencia. Also, many thanks to our co-host here, Carlos Arando Herranz. Jose will talk about a topic that many of you are quite familiar with, which is field programmable photonic gate arrays. And as you also know, he is really one of the pioneers of the field. So you're going to hear from one of the best. Should be a very good talk. Let me give you a little bit of background. Jose is a professor in photonics at the University of Politecnica in Valencia in Spain, and there he leads the Photonics Research Laboratory. His education is in telecommunications engineering and in physics. And as many of you know, he has been focusing on these programmable photonic circuits, but also a lot of work in microwave photonics. So he's a fellow at the Institute of, he's a fellow of the IEEE. He's a fellow of the OSA and the Institution of Engineering Technology, IET. And he actually, oh, can you hear me? Yes. And he started two companies that are actually doing really well. You should check them out. One is VLC Photonics, that focuses on special purpose photonic circuit design. And the other is iPronics, which is a programmable photonics company. So have a look at those very cool efforts. So with that, so great to have you, Jose. Looking forward to your talk.
Okay, thank you very much, Dirk. Thank you very much for a kind presentation. And first of all, thank you for inviting me, guys. I'm very honored to have the chance of giving this talk today. And first of all, what I would like to do is to give a very short outline of what is going to be my talk. I hope my internet connection remains stable, and you can hear me and see me with enough quality during the presentation. So also welcome to everybody who is not either in the Boston area or maybe in Western Europe. If you are in other parts of the world, good evening, good night, or whatever it applies. Okay, so today I'm going to talk about the field programmable photonic gate array and as an example of an emerging field, which is programmable photonics. To do that, I'm going to start with a short introduction and motivation to programmable photonics. Why do we need it? Is that necessary? And then I'm going to go in very brief, this small number of view graphs. I will try to give you some of the advantages that programmable photonics brings to try to convince you. There are many flavors to programmable photonic circuits. And in our case, what we think is a very interesting approach is to do something that has been already carried in electronics, similarly, which is the field programmable gate array, but in this case in photonics. This is going to be the big part of my talk, and actually I'm going to spend most of my time there trying to describe you the many different aspects that this device involves, but also as well the applications. And I'm going to also try to give you some of our experimental results, Some of these are already public. Others, which I will not be able, unfortunately, to give today, are still confidential. But I hope to cover many of interesting aspects and at least raise your curiosity. And then I will go into a summary and conclusions. After, I'm open to your questions at any time, so please feel free to put them forward. So yeah, regarding programmable photonics, why would we need photonics or programmable photonics at all nowadays? Well, we all experience as users the emergence of a number of applications which are constantly flowing. Some of them are listed here. Some of them were not even in our minds, let's say 10 years ago. And despite of that, they are actually now hot topics which are requiring a constant increase in bandwidth and processing power. Okay, so up to now, during the last 50 years, we have enjoyed a fantastic era where electronics has been able to cope with all our processing needs, because there have been several scaling laws that have been fulfilled during all this time, and in particular Moore laws and then our scaling laws. However, nowadays there is a situation where there are signs that these scaling laws are starting to saturate and may no longer hold in a few years. And yet these applications are constantly emerging, and it's a little bit more scary. There might be some others behind that we are not aware now that will actually require even more bandwidth. So if electronics is going to have some problems in coping with this ever-increasing requirements for processing and bandwidth, we need to find ways on technologies to cooperate with it. And photonics actually is particularly interesting alternative because it's complementary to electronics, and it can also be integrated on chip. So photonics, and in particular integrated electronics, integrated photonics has been around for many years now, maybe 30, 40. And has had a slower development as compared to electronics. And nowadays, more or less, I would say that 95% of photonic integrated circuits that you can find are application-specific circuits, which have been successfully integrated in many applications, but suffer from several limitations. One of them is their time to market, and the other one is the fabrication cost. It takes a lot of time to fabricate your application-specific circuit, and you might not be successful the first time that you do, so you have to go through several cycles. So one of the ways to think about how we could incorporate photonics in a real agile way, so to let's say overcome these limitations, is to follow a very similar path to what was done in electronics like 40 years ago, by the way. And this is to go to programmable circuits. And of course, we believe that the time for programmable photonics has already come. And if you look at the historical development of electronics and photonics, you will see that we are probably in the period where we can feel confident that a solution on integrated photonics will kick off successfully. What I'm showing you here is a little bit of summary of the main developments and eras in the development of electronics technologies. And you see that from the very first transistor designs to the era where the general purpose and programmable systems came into market, we had to wait for at least around 40 years, more or less, roughly, and in particular, the surge of the FPGA device. And if you compare to photonics, you will see that the situation is similar, although it's a little bit, there's of course a delay because photonics is a little bit delayed in comparison with electronics. But if you see the steps, everything indicates that we might be as I said before, in this part of the time where we can think about developing programmable solutions that are technically and economically feasible. So this is the motivation. Right. So what is programmable photonics, and what is the rationale behind programmable photonics? Okay, where here we are always talking about flexibility, saving costs, saving time, etc. So in any technology, adding reconfigurable components increases the power for flexibility, the power of reusability, making more versatile and systems, etc. You can think about, for example, the space industry, where SpaceX is trying to make these reusable rockets, where the rationale is actually to substantially reduce the cost and development times of these rockets. Even if your rocket is very expensive, if you can reuse it many times, then the cost per usage is heavily reduced. So that's something that needs to be evaluated in any technology, but in photonics or in communications in particular as well. I have to say that in telecoms, this is not the first. Programmable photonics is not the first attempt to do this kind of systems. You all know, for example, in electronics, FPGAs and ASICs. In telecom networks, we have this concept of software-defined networks, where you have a pool of resources and you make use of or optimize the use of these resources dynamically by programming. So you can have your ad hoc topologies, you can do capacity reconfiguration, etc. In radio, we have the software radio for instead of specific receivers. So we have general purpose programmable receivers that can be actually activated and to provide several functionalities by programming. So it's not new at all. And actually, in photonics, for example, if we talk about programmability and reconfigurability, we have further advantages that I'm going to try to show you with a very, very simple example. I guess that most of you are photonic guys, so you will be able to understand this perfectly. Suppose that you are given the task of designing a very simple circuit, like a ring filter. You want this ring filter because it's a notch filter, and you want to get rid of, want to use it to get rid of some signal at the given wavelength. So you do your design. You know that this is an infinite impulse response filter. You're given your specs. You do your ring design. You compute your waveguide, cavity length, coupling factors in the cavity, etc., and you do your design. You produce your layout, your mask. You go for fabrication. You go to foundry. You spend many months and many dollars with that, and then you get your dices from the foundry, and you start testing, and then you find out that it doesn't work. Doesn't fit the specs, and then you have to go back and refabricate, and maybe you are not successful again, and so on. Okay, so this takes a lot of time and money. Okay, And this is one of the reasons why programmable electronic circuits were also invented at the time. Well, if instead of that, you allow for some small reconfigurability, that is, okay, I'm going to do the same design, but I'm going to incorporate some tunable components here. Instead of doing fixed couplers, you do tunable couplers, and you allow for a phase shifter in your cavity. And then the design is not much more complicated, but then you go again to your fabrication and wow, it's wrong again. But then you have the possibility of acting over your circuit elements and probably change it without needing to go back to the foundry. You don't need to redesign that, hopefully. And this is actually one of the big values of reconfigurable photonics and programmable photonics. It allows you also to save time and save costs. Okay. So with that in mind, programmable photonics has evolved during the last years from the very simple reconfigurable application-specific circuits like the ring that I showed you before, to some a little bit what we call few functional circuits, where you have a fixed topology. Really, you can identify, for example, rings or whatever, but you have reconfigurable elements. And it turns out that with these few functional aspects, you can do 3 or 4 different tasks. Not all of them with the same degree of quality, but it's enough for 3 or 4 functionalities. Then I guess there are many people here working also on quantum. So there's a lot of interest in using multi-port interferometers for linear transformations in the quantum operations. So these are structures where you incorporate your tunable elements, in this case, phase shifters and couplers, and you do these multi-port interferometers to do your linear transformation, and your signals go feed forward, and with that you can do these transformations. One step further is if you do programmable waveguide meshes, where it's very similar to the multi-port interferometer, but in this case you connect your phase shifters and your couplers in such a way that you allow for feedback. So actually the waveguide mesh can provide feed forward and feed backward propagation. That would be, let's say, like from very simple circuits to subsystems. But if you want to go a little bit further, then you can think about, okay, I'm going to use this, let's say, waveguide meshes or multi-port interferometer as a basic subsystem, and I'm going to surround it with other special elements. Like in electronics, we have the FPGAs, as I will show a little bit later. They are surrounded by what we know as IPs or high performance blocks. These are specific circuits. So actually you have a core that is going to provide interconnections of these high performance, between these high performance blocks. They are going to provide also interconnection to input-output ports, or even they are going to be able to emulate internally circuits. So these are more or less the main steps of programmable photonics so far. Okay, so let me then go into the core topic of the talk today, which is the field programmable photonic gate array. What is that? Okay, let me go first of all to the electronic FPGA. Electronic FPGA was patented around 1989, or it was a little bit earlier, developed a little bit earlier. And actually, I show you a photo of the inventor, of Ross Freeman, and also a very simple layout of the patent application. It was conceived as a device that interconnected the configurable logic elements that you can see here. These are the configurable logic elements, quite complex interconnection, wiring, I/O paths, etc. At the beginning, it did not include the high performance blocks, but the idea is that these configurable logic elements are subsystems that are composed of or built using irreversible 2x1 gates defined by truth tables, like the ones that you know from Boolean algebra, like the N and or X or NAND gates. Okay, so inspiring this in this concept, the FPPGA is similar, but it's a little bit different. FPPGAs are built again using it's an interconnection of some kind of computing elements, which we call gates in this case, and these gates are 2x2 reversible unitary gates, and the condition is that they have to implement a unitary transmission transformations. In this case, though, the difference is that we are not using digital Boolean algebra. We are going to use analog algebra. We are not going to use irreversible gates. We are going to use reversible gates. So how do you implement these gates? Well, these gates, these U2, we call them U2 transformation gates, is an arbitrary transformation, but it turns out that for you, for the quantum guys, this will be easy to understand. This is a rotation, an arbitrary rotation around the box sphere. And actually, you can come from whatever input state you have, and you want to go to an output state, and it's defined by a rotation around an arbitrary axis. It turns out that whatever this axis is, you can always decompose this rotation into a product of 3 rotations around 2 non-parallel axes. So this is the theory, and then one can think about the implementation. And in this sense, nature and technology, both of them have been very generous, because it turns out that it's very easy with very simple photonic components to implement rotations about the main axis, the X, Y, and Z axis. You have 3 examples here. Sorry, when I show how you can implement a rotation around the X axis with a tunable, with a directional coupler, a rotation around the Z axis using a dual rail phase shifter, and a rotation around the YX by actually using this Euler transformation. It's very easy. There are different flavors to do this. You can do this using 3 dB fixed MMI couplers and intermediate phase shifters, or you can use a directional coupler, tunable directional coupler with external phase shifters. So these are components that are very easy to do in integrated optics. So the idea would be, okay, if I can do these very simple transformations, then I can do whatever arbitrary transformation I want around any axis. But it turns out that the ones that require the lower number of components are those that are done around the X, Y, and Z axis. This is what we call minimal circuit architectures for gates. And actually, what this implies is that if you want to have a universal 2x2 transforming gate, either you can implement it using this alternative, which is a rotation around Z, a rotation around X, and a rotation again around Z, or the same rotations, the same scheme of rotations, but you substitute the X rotation by a Y rotation. And any of these two, the number of elements that you require is the minimum. And this is very important because this makes a difference when you're going to construct a photonic integrated circuit, because then footprint is a very valuable resource. Now, once you have these, the gates, you turn up. Okay, how do I interconnect the gates? Because in the overall 2D diagram that you saw there, the interconnection was very arbitrary. Okay, Let me skip this one. Actually, it turns out that you can connect these 2x2 U2 gates in different forms. I'm showing 3 of them. And it turns out as well that you can establish an isomorphic transformation between these schemes for connections and different geometries for what we call waveguide meshes. So you can interconnect the gates like this, and you will have an isomorphic square waveguide mesh, or in this way you will have a triangular, or in this way you will have an hexagonal pattern, a 2D hexagonal pattern. So the message here is that you can implement this core of the FPGA by using integrated optics waveguide meshes. Okay, so this is going to be the core of the FPGA device hardware. Sorry. So I'm showing here a beautiful picture of the hardware concept of FPGA. We have our core. As you can see here, I've written or I've drawn this using an hexagonal waveguide mesh, because this is the one that provides the most efficient operation in terms of a variety of figures of merit. And you have this core here. This is the photonic part, the core, the input-output. You will have input-output ports mainly from optical fibers coming and incoming from the chip. This core is surrounded by this high-performance blocks, of which I will talk a little bit later. But then you have also an extra hardware, which is a control electronics and probably RF interface if your application is going to interface with wireless or RF signals. Okay, so that's actually, here is the core. So if you go a little bit further and you want to see how the core, the photonic part is made, this is a layout of an hexagonal waveguide mesh. And here, as you can see, there is this the IP surrounding the core can be a variety of application-specific circuits. And I'm going to talk a little bit later. Of course, it can also be modulators and maybe something as complex as a photon source or a detector. Okay, there are different alternatives. So actually, the FPGA, the photonic core, what it's going to do is either provide interconnections between these high-performance blocks, as you see here. Okay, actually, in this example, the waveguide mesh is just making interconnection. Okay, but you can also use it to emulate circuits internally. You don't need to use, for example, the external blocks. You want to emulate some circuits inside here, you can do it as well. Or you can do both things. You can emulate part of your big system in a circuit here, and you can also connect. Just to give you an example, let's say the high-performance blocks that you can include here can be very different. And though it is true that the FPGA aims to be a general device, it would be specialized probably to different application fields. This is not new because it has been also the path that has been followed by electronic FPGAs. They started to be a very generic product, and afterwards they ended up with, you have more communication-specific FPGAs, other more for control or whatever. But in any case, the degree of the number of the variety of high performance blocks that you can include here, it's very high. They can go from external filters that you would like to put outside because they are high quality, because they have slight different period, and you want to leverage and use vernier effect, for example. They can be more complex. They can be delay lines, dispersive delay lines. They can be beamforming networks, etc. Or even AWGs, because you want to provide an additional dimension for operation in the wavelength domain, for example. So this is the idea of complementing the core with these high performance blocks. On top of that, of course, you need hardware is not enough. You need software, and software at the very beginning you might think is okay. I need software to program my circuit, which is true. Actually, you need to program your circuits, and you need your software to do that. But you need software, a software suite, to do more things. And for example, again, we are translating this concept from the FPGA world. In FPGAs, in electronic FPGAs, you need at first to have algorithms that run over your FPGA before you start to use it and configure it. I mean, to put it on a starting state, or to characterize the operation, to test dynamically that everything is working correctly, that all your transistors are properly biased, etc. This is even more important in photonics, where you have to take into account that you have to protect your components from deviations due to thermal effects, for example, from crosstalk, etc. Self-configuration, in these cases, when you want to use your program, your device, but the starting point of your internal components, your couplers, etc., is unknown. So you need to know what is the internal, let's say, bias-free operational point, and then you have to compensate for that, and then you can start your programming. You have to include routines for establishing your circuits, which is the connection that you want to do to employ between input and output ports. Even if it's a connection, if it's a circuit emulation, you need to know where you want to put it, and on which resources are you going to manage. And to do that, you need to use optimization routines that actually can have very simple or very complicated cost functions, where you take into account one or a linear combination of different restrictions. So the idea is that despite the kind of circuit you want, programmable circuit that you want to implement, even if it's a very simple ASPIC, or even if it's an interferometer or an FPGA, you need all these routines. At the same time, FPGA is very popular because in electronics, because it allows you two modes of operation. One is the kind of developer mode that allows you to do your own customization of the system. But at the same time, you need also a set of routines that will assist you in more complicated designs. But at the same time, it must operate in a way that a user that is not heavily trained, does not know a lot of photonics, etc., can do a lot of things with integrated circuits with very little effort. Okay, and definitely not needing to know what is going in the insides of the photonic chip. So this is the part of the programming suite that you need to do. Let me give you a couple of examples to show you how versatile this concept can be. What I'm showing you here is a layout of an hexagonal waveguide mesh. Here, what we are trying to do is to program this layout. So it provides you with a beam steering capability, where your incremental delay between the different parts of the beamforming ranges from 0 to a given multiple of the unit length. The unit length being this part of a circuit. Okay, so you can see that with the same circuit with different programmings, you can have the same input, the same 8 outputs, but the circuit is configured in such a way that the delay difference between the different outputs can be tailored at will. You don't have to change anything in your hardware. It's just you change it by software. This is another example of what I call the auto-routing functions. This is how, for example, if you want to establish a connection between an input and an output port in your waveguide mesh, and the different options that you have. If, for example, you have one of the connections fails because there's a coupler burns out or whatever, you need to find out alternative paths. Or if you want to establish just a connection between two extremes and you want to force these to follow some restrictions, maybe delay, maybe losses, etc. You have different alternatives, and then the routines can dynamically calculate which is the best path. If you want to change, you want to maintain your circuit, but you want to change it into another part of the available footprint in the chip, this can also be done with these routines. So a third example I'm going to show you that you can find in one of the papers that I'm showing you below is one of the optimization techniques that we employ, for example, for implementing filters with the FPGA, for example. And the way you do this is that you specify a filter mask. You know nothing about the filter, about the FPGA. You need no prior knowledge of what is the value of your input values of your couplers, etc. How they are when you start programming the circuit. You just specify your mask, and by running the optimization routines, the system evolves so it matches as best as it can to the required phase mask. Filter mask. What you see here are different examples of this capability, and you can see a little bit more. You can have a little bit more information in the paper. The point to which I'm trying to make clear is that a FPGA value resides, of course, in a very powerful hardware, but actually the added value it's on these routines and on this reconfiguration and programming software. This is where the big value resides on this concept. Okay, so a final example. This is an example where we are setting. We have this hexagonal waveguide mesh, and we are specifying a dispersion compensator, which means that you would like to have on your available spectrum a flat passband and this linear group delay characteristic. And actually, I'm gonna go back a little bit so you can see how the configuration routine starts to run until it converges. And what is actually this routine is actually doing is changing the values of the phase shifters and the tunable couplers in the waveguide mesh. Again, you can find more details in the paper. Okay, so before I go into the applications, I want to finish with this very general concept about the FPGA. As I hope to have shown you, it involves a lot of layers. Okay, we start with a very low level layer where we have our photonics. We may have an upper layer where we have electronics, and we might have both analog and digital electronics. Analog, if we have RF. Digital electronics, because all this control circuitry is run on digital circuits, of course, and microsystems. And we have another layer that involves all the packaging, because we need to have a device that actually incorporates integrated photonics and the electronics. Nowadays, this is done discretely, but hopefully, maybe if we find a suitable CMOS compatible overall platform, we might be able to do this on chip. And on top of that, we have this very, very generic and very comprehensive programming layer, okay, where we need to do a lot of, or run a lot of optimization algorithms and software routines. Some of them are low level, some of them are high level. And finally, well, we will have the interface with the end user, okay, which can be something as can include this development board and also all the environment. So, from a technical point of view, I think it's very exciting. But what about the economics? Well, the economics, this is something that is very similar to electronic FPGAs. As it happens there, using FPGAs allows you to distribute among all your end users the non-recurring engineering costs. So that means that the cost that you incur in the first design of the product or the FPGA is really low, because it is shared among many users. However, if you do an ASPIC, then each time that you do your design, if you have to change, especially all your costs, you start almost from scratch. So it turns out that if you don't have a huge volume of circuits to serve, the programmable PIC solution is always advantages over the ASPIC approach. Okay, so this is the main concepts. Now I'm gonna delve a little bit on what applications can we find for this programmable, for the FPPGA or programmable circuits in general. Okay, so I'm going to try to cover just a few of them. I'm not trying to. We don't have results for all of them, just for a few ones, because we're still on an early development stage. But our idea is to have the FPGAs on many applications. They can run from everything that connects wireless, 5G, for example, and fiber or wired segments. They need an interface between these two worlds. So we think that the FPGA is a very well-suited device to do things like RF filtering in this conversion, arbitrary waveform generation, frequency tracking, etc. But we also think about other applications like beamforming, like probably lidars, and other more specific to communications, like probably data centers, of which I will speak a little bit later. And this is a general perspective of that. Having said this, let me try to think about, to illustrate a couple of examples. Here I show you one of the first prototypes that we have. Nowadays we have a more evolved chip, of course, but it's still on testing. But this is a very simple waveguide mesh with 7 cells and with a PCB, and of course it has its own control system, which I don't show here. But just as an example, I want to show you how you can use your programming to make this system emulate different circuits dynamically on time. What you're going to see here is a very simple example where we use this limited system to implement one kind of filter, then to change to a second filter, and then to implement 2 different filters using the same footprint. So this allows you to show you, gives you a demonstration of the reconfiguration, but also about the possibility of doing parallel circuit construction. okay? So what you are seeing here, actually, let me try to stop it. What you're going to see here, first of all, you see the waveguide mesh. These are experimental results. We are trying now to implement this ring filter, which is seen here. And what you will see is that when it ends up, it will transition to a second configuration where we are actually, this is the ring filter. When this is implemented, okay, we set a second device where this changes to sorry. Let's just go back if I can. It seems to be okay. Right, something wrong happened here. Sorry. So actually, it will start to implement a ring cavity, as you see here. This is configuration 1, and it arrives to configuration 1 from an arbitrary input state. Okay. So once this is implemented, okay, then we implement a Mach Zehnder interferometer. So you see it on the second trace here. And once this is implemented, we evolve that to implement 2 separate circuits, a ring and a Mach Zehnder. You will see the ring here and the Mach Zehnder here. Of course, this is a very simple implementation, but it gives you an idea of the potentials of FPGA. That FPGA was waveguide mesh was made in silicon. We can make them also in silicon nitride, which might be also very interesting for low loss applications, maybe in quantum. Similar waveguide mesh with a more waveguide with more cells. And here we have used it for other applications, filtering and digital, etc. I'm not going to comment that a little bit further because I'm running out of time. Sorry. More applications. Yeah, for example, for data centers, you need a core which could be flexible, which you would need it for interfacing either CPUs or hybrid processors, which are going to be broadband. And you need something which is very agile and is able not only to do this interconnection, but probably do an intermediate tasks within this interconnection. So in this context, we think that the FPGA can be very useful, not only for this pull and compose of resources, but also for doing intermediate processing tasks within the connection. For transceivers as well, it could be useful because in coherent transceivers, one of the main problems that we have is that hybrids, for example, they are not usually perfectly matched. They are not in equilibrium. Okay, they have imperfections. So if you have imperfections, actually, what happens is that you have an considerable increase in noise. At the same time, you might wish in your transmitter to change the spectral shape of what you are transmitting. So it would be useful to have the possibility of spectrally shaping your signal once you have modulated. Okay, so there are a lot of things that can be done. In the case of the transmitter, as I said, you can incorporate with FPGA, you can incorporate different high performance blocks, which would be traditional laser or modulators. But then internally, you can add tunable ring filters to increase the line width to improve the line width of your laser, or even a channel shaper if you want to do some kind of spectral or Nyquist shaping before you go out of the link. In the detector, this is very important. Once you mix that with the input signal with your local oscillator, you can even implement here emulated tunable ring filter to increase the line width and suppress the phase noise of your local oscillator. And even here, you can emulate 90-degree tunable hybrids. And because this is reconfigurable, you can guarantee that you're going to reach the sweet spot of of the 3 dB division. That is what you need in coherent detectors. So this is one of the things that we think is useful. Of course, you guys, many of you work in artificial intelligence, so the FPGA, the waveguide mesh, can emulate matrices because it can emulate interferometers and, of course, the spectral value decomposition. And moreover, you can think also to set your systems in order to emulate like kind of different quantum gates in which the FPGA allows you to provide you with ports to not only to have your qubit results, but also to examine your ancilla qubits, etc. And why not set different interconnection paths if you want to, for example, emulate something like a random walk system, or even at the same time with combined with other operations. So all in all, in this case, the high performance blocks that we call quantum high performance blocks would need to be something different. It could be a photon per source, or any other kind of external quantum device that you would need to either generate or detect your photons. Okay, yeah, I'm just finishing now. Of course, we have different flavors, different possibilities of combining high performance blocks and different applications for which we think that we can engineer the device to do all these different applications. I have to say that it will never be the same quality as with an application-specific circuit, but this is not a big problem. This also happens in electronics. FPGAs usually don't do it, don't perform as well as application-specific circuits, but they are very convenient for many applications. Right, so I hope to have convinced you that programmable photonics is going to happen, and also try to show you some of the commonalities that it has with electronics, but also some of the differences. And more importantly, it is analog. Don't forget that we are not aiming to absolutely replicate electronic FPGAs. Electronics works with electrons, which are fermions and can be stopped. So you can do memories or whatever. Photonics works with photons, which are bosons, cannot be stopped. So forget about these kinds of memory-based computations. Computations can be very, very fast, but they have to be on the fly. This is what I believe. But in particular, I have focused on this field programmable photonic gate array. That is what we are working on. And of course, I didn't have time, but what comes next is, of course, the circuits that we are working now are scaled versions of what I've shown you. They include much more, many more, tuning elements, many more phase shifters, etc. And this puts a lot of challenges in terms of managing the losses, managing connections, many electrical connections, managing crosstalk from thermal crosstalk, photonic crosstalk, etc. But we think that these challenges can be solved in the near future. If you want to know more, you can check the papers. Of course, there are a lot of other groups that have published very good papers on the subject, and you can check this very nice tutorial paper on programmable photonics, which we co-author with Dirk here. So thank you very much for your attention, and I'm sorry to have a little bit gone a little bit over.
That was fantastic. Thank you so much, Jose. So let's hear some questions then.
Hi, Jose. First of all, I think this is really cool.
Maybe introduce yourself first.
Oh, sorry. This is Jordan Goldstein. I'm a graduate student in Dirk's group. Thanks for the great talk. I think this is really cool, promising, and I can definitely see a market for this technology. I think if you were able to have both the programmable photonics and OE, EO, sort of like detectors and modulators, and electronics, sort of like programmable electronics, all in one die or all in one package, I think that would really open up the application space a lot, because then you could do like photonic controlled packet switching. A lot of communication protocols would probably would benefit from having that sort of technology, where you can just you have like this one package, and then you don't have to deal with the, say, discrete photodiodes. You can just plug in your wire bonds and your fibers. Is that something which you guys are planning on working on, combining both the electronics and the optics, and interface between those in one chip?
Okay, thank you very much. That's a very good question. Actually, we always insist that programmable photonics is a cooperative and not a competitive technology. So it needs electronics. So actually, it not only needs electronics, but it also opens the possibility of doing a hybrid approach where each technology can be leveraged to do what is best at. So actually, yes. So the idea would be to, the concept, the theoretical concept and the developments are the first step. But of course, there's a lot of work to be done in the technology. Let me put you an example. One could think that silicon, silicon, in my opinion, is the best platform to do this, because it's CMOS compatible, and of course it opens the possibility of integrating your photonics and your electronics, and as you said before, not necessarily the electronics be there to operate or bias the photonics, but also to do some information exchange.
Yeah.
Packet switching. I did work several years ago on level swapping and at that time that was not possible because we didn't have the possibility of concentrating everything in a very small footprint. So the latencies and everything is are very high. So yes, that's actually one thing that we are looking forward to be able to develop. Thank you.
Thanks.
If I can follow up on that question, so that I think implies that you have to do a tighter co-integration of the electronics with the photonics. Can you already, it's probably similar for you as it is for us, that the number of electrical connections to these circuits is in the hundreds, many hundreds. And we have to integrate some sort of logic probably to manage that complexity in future chips directly with the photonics. Do you have can you comment on your thoughts on that?
Actually, yes, we would need to scale the number of units, let's say, of phase shifters, etc., elements into the many hundreds, and probably go today is a little bit of challenge into the few thousands. And this is going to require a huge effort in the control, but this is where electronics is very good for. So actually, we may have a problem more related to how do we do the electrical interconnections and how do we place our electronics. So actually, the control is efficient in terms of this wiring, but also on the latency. It's a big technical challenge, indeed, very big.
Yeah.
Hey, Jose, this is Matt Zimmerman from MITRE. I was kind of wondering, this might not be something you can answer, but I was wondering where industry is going with this. Like, I'm an FPGA guy, and I know Xilinx and Intel, they dump billions into their FPGAs and their development software. And I'm wondering if they're getting involved with photonic, basically like photonic FPGAs or field programmable photonic gate arrays, or if they're just focused on electronic FPGAs.
Okay, I don't think I'm not sure if I catch very well all the audio. Sorry.
Sorry about that. I just was wondering if Intel or Xilinx or any big industry companies were investing in this.
Okay, not that I am aware. But you know, you guys come from more or less from MIT, so you know that when you have big innovations, the big companies don't usually, you know this book by Clayton Christensen, and you know that usually these innovations really
Innovation dilemma. Yeah.
from the lower end of the market. So big companies are not very interested at the beginning, and maybe this is also the case. But if this is successful, of course, they will be interested in actually approaching to this concept.
I mean, that's you have startup companies that came out of your group that are disrupting the space that way, and then maybe bigger companies will look to partner or acquire.
Yeah, that's always an option. Yeah, you know that there's always a room for growing. You know, it becomes some deep tech. You reach a point where you need more resources, of course.
Yeah. Okay, we have a question here from Achint.
Hi, Jose. Thanks a lot for this wonderful talk. Just to follow up on that, I was wondering about the commercial status of this technology now, or when do you expect to see the first FPPGAs to hit the market? What's your opinion?
Yeah, I would like to say you that as soon as possible. It takes time because you know it's like with any new concept, you need to we need to validate that. We need to do some kind of initial product development, and we need to validate the concepts. Need to validate our hypotheses. Our idea would be to have something around the end of next year.
Okay,
That
thanks.
being 2022. Yeah, actually. Roughly, but it depends because you rely on foundries and you pray that they don't shut down because of the COVID or whatever, and you never know.
Question from Ronald.
Oh, yeah, Ronald.
Yeah, thanks for the talk. I was wondering, you said one of the applications for wireless signals and signal processing. I was wondering what phase shifters you use. Do you use a mix of fast and slow phase shifters, or like to have a modulator and bias, or like to have some section of it be a modulator, some section of it be a filter or something? And does the phase shifters you use limit the I guess the broadband applicability?
Okay, thank you. That's also a very good question. What we are using now as phase shifters is a Thermotics phase shifter. Okay, these are in principle they are not very fast, but for many applications you don't really need extremely fast switching mechanisms. For others, yes, of course. And in thermotic phase shifters, they are slow and power consuming, of course. But there's been quite an improvement. So this power consumption has gone below 1 order of magnitude and probably will go 2. And if you want faster phase shifters, then you have to think about other faster mechanisms. Of course, you can think about plasma carrier devices like PN junctions, which will include which will actually introduce losses, and also some kind of coupling between amplitude and phase. And but having said that, we think that in the near future we will be able to incorporate active elements even in silicon photonic chips. So we will be in principle be able to use them to compensate for losses. But also you have, there are also several techniques for transfer printing to silicon chips, which include not only actives, but also probably other fast modulation materials. We'll see. At this moment, I don't really, I mean, we have two paths for the phase shifters. One is if you want really low consumption, then you want to go for kind of non-volatile schemes where you are not consuming power if you don't change your settings. You only consume power when you change your programming. And at the other side is the fast modulation. If we don't think about very fast, I mean, we are not working with, for example, digital logic. So we don't need to take decisions, and we don't need to do a very extremely fast programming. So I don't think that, for example, for, as you mentioned, for RF-Photonics, we may need to steer a beam at the let's say not very high speed. I mean, we are not going to need it at nanoseconds at this time. It would be useful, but you can live with hundreds of nanoseconds, and for that, other technologies are most of the technologies that are available now are fine. But it's true that we will need to develop this, consider this fast switching or fast phase modulation alternatives. Yes.
Adrian?
Yeah, hi. Great talk. I was wondering, so you're focusing on silicon photonics at the moment, but there are many applications in quantum and biophotonics, for example, that would require visible light modulation as well. Are you looking at other platforms that would support different wavelengths?
Yes. I showed you in the first the first chip that I showed was a silicon photonics, but the second one, which I was running out of time, so I couldn't actually take a lot of time on that. Let me see if I can show you the view graph. It's a silicon nitride. Okay, was not extremely good silicon nitride chip, but it's a silicon nitride. There you will see something that is curious. We call them this folded. Sorry, let me go back. Yeah, these are folded Mach Zehnders. If you have a look at the layout, you will see that the Mach Zehnders are a little bit like, you know, the waveguides are folded. You see this in the upper, in the lower right hand side of your view graph. You will see the Mach Zehnder arms of the gate in red.
Lower thermooptic.
So they are not straight. They are a little bit they are folded because of the technology requirements. You know, it's a low contrast, so we need to do something a little bit different. But yes, we can change. And I didn't show here, but there is another. We actually, in our new designs, we don't use this geometry that you see. You don't see the hexagons. We use, like we call, flattened designs, where actually you will see the footprints of the Mach Zehnders are they are like shrink, and you don't see actually the geometry. There's the real geometry is a mesh, a waveguide mesh of hexagons. But since they are like squashed like an accordion, you know, so they occupy much less footprint, and actually this helps for technologies also that have a lower contrast. So in answer to your question, yes, we are actually. We are designing this waveguide mesh not only in silicon nitride, but also in other platforms as well.
Okay, thanks. Yeah, I guess the problem here is the lower thermo-optic coefficient of silicon nitride, so you have to make them
Yeah.
the arms a little bit
Yes.
larger. Yeah.
Yeah,
Thank you.
For example, for sensing applications, you might not need so much. You might not need so much speed, you know, and maybe. You know.
I have a couple of questions. As you keep scaling these circuits up, how do you expect to deal with things like optical loss and parasitics because of your recirculating geometries?
Okay, that's a good question as well. Losses by what we want to do is to the way that we think about compensating losses is by using amplification stages, but this will be on chip. Okay, the idea would be that you cannot put the amplifiers inside the waveguide mesh, because then you destroy the geometry and then you destroy the uniformity. And on the other hand, you don't want to have the amplifiers inside because they can generate loops or lasers, etc. You don't want that. So actually, we're thinking about external ports, external areas where you actually place your amplifiers. Now, the way to place those amplifiers probably would be, for us, the most interesting option to investigate now is diffuse transfer printing, because that would allow you to have a neat integration. Turning to your second question, this is also a very interesting topic, because one of the things I didn't talk about today is that when you think about programming your waveguide mesh, you are basically focused and interested in programming your circuit. You say, okay, I want a ring filter or beamforming network, etc. So you focus on this particular layout, and you program your waveguide mesh to do this functionality, some elements of your waveguide mesh to do this functionality. But you still have a lot of other elements which will not take part in the circuit, but nonetheless you can program so they can take out noise. You know, you can, I'm trying to find the word in English, like drain, you know, they drain unwanted parasitics, for example. We've actually prove that actually this can be done, and the performance of your design can be improved. There is an Optical paper, I think it's already quoted in the view graphs. If you go there, you can find it. How we do program the external elements outside the circuit, so they optimize the noise performance, and they help to evacuate your noise.
Right, thanks. Thanks.
Okay.
If we don't have more questions, I think we can stop here and start with the one-to-one meetings. So thanks again, Jose, for very nice.
Thanks very much. If I can make one comment or suggestion, I think in honor of the great work by Jose and his country in Spain, we should perhaps consider adopting the Spanish spelling of photonic in FPGA, Photonic Programmable Gate Array. So we solve that problem. Thanks again, Jose.
That's very kind. Thank you.